Welcome to the AIAA Dryden Lecture in Research. I'm Laura McGill and the chair of the AIAA Honors and Awards Committee. The Dryden Lectureship is one of the most prestigious lectures bestowed by the Institute. Since the inaugural lecture in 1961, it has been a catalyst for sharing research advancements and knowledge. This premier lecture is named in honor of Dr. Hugh L. Dryden, a renowned aerospace leader and the director of the National Advisory Committee for Aeronautics, fondly known as NACA, as well as the first deputy administrator of NASA, when the agency was created back in 1958. The award emphasizes the importance of basic research in advancing aeronautics and astronautics. It is now my very distinct honor to introduce to you the winner of the 2022 AIAA Dryden Lecture in Research, Professor Anthony M. Waas, my colleague. First, I need to say a few words about our esteemed lecturer. Professor Waas is the Richard A. Auhll Department Chair of the Aerospace Engineering at the University of Michigan, Ann Arbor. He is also the Felix Pawlowski Collegiate Professor in Aerospace Engineering and a Professor of Mechanical Engineering. He's been with the University of Michigan since 2018. Prior to that, he was the Boeing Egbert Endowed Chair Professor and Department Chair in the William E. Boeing Department of Aeronautics and Astronautics at the University of Washington in Seattle. His current research interests are robotically manufactured lightweight structures, computational modeling of composite structures, 3D printed structures, damage tolerance of composite structures, affordable textile composites, and data science applications in modeling of materials and structures. Professor Waas was at the University of Michigan from 1988 to 2014, prior to joining the University of Washington in 2015. He is a fellow of the AIAA as well as, it's a long list, the American Society of Mechanical Engineering, the American Society for Composites, the American Academy of Mechanics, and the Royal Aeronautical Society of the UK. He is a recipient of several Best Paper Awards, the 2016 AIAA ASME SDM Award, the AAM Junior Research Award, the ASC Outstanding Researcher Award, and several distinguished awards from the University of Michigan, including the Stephen S. Atwood Excellence in Engineering Award, one of the very highest honors for an engineering faculty member at the University of Michigan. He received the 2017 AIAA ASC James H. Starnes Jr. Award for seminal contributions to composite structures and materials and for mentoring young students and other professionals. In 2017, Professor Waas was elected to the Washington State Academy of Sciences and in 2018 to the European Academy of Sciences and Arts. He is also the recipient of the 2020 AIAA ICME Prize and the 2020 ASME Warner T. Coiter Medal. Recently, Professor Waas was elected to the U.S. National Academic's Aeronautics and Space Engineering Board. Professor Waas will now speak on the topic of digital tools for design and analysis of composite aerostructures. Please join me in welcoming Tony Waas to the stage.
All right, thank you everybody for attending this talk. Thank you, Laura, for your kind words in introducing me. I'm really honored to receive this award. I have great memories of this meeting, which started out as SDM for me and has continued and is called SciTech today. It's a great forum for technical exchange. So before I start, I want to thank many people, most of all my students, but especially Drs. Piñadas, Thorson, DeMello, Xiaolin, Paul Davidson, Ashit Joseph, and Ming Nguyen, my graduate student, who has made major contributions to what I'm going to talk today. I also want to acknowledge my sponsors. It's a long list. I will not mention names, but the names are up there. Many of them are in the audience today. And the universities of Washington and Michigan for their support during my career there. And lastly, but not the least, my family for being a source of strength, love, and support. Isaac Newton wrote in 1675 that it is by standing on the shoulders of giants that you make advances. So that saying goes for all composites researchers who are here and who are also listening by Zoom. I want to thank all of them for their tireless efforts to develop better, lighter structures. And believe me, there's a lot that we can still do with these materials that I'm going to talk about. So the overview of my talk, I'm going to start with motivation, digital tools for composite aerostructures, the building block approach that is used in aerospace engineering, and then provide examples of performance modeling and manufacturing, digital tools for these two areas, and then I'll conclude. This audience does not need an introduction to this subject. All of you are aware of the increasing uses of different types of composites in a wide variety of industrial applications, aerospace being a prime mover in this area. In aerospace, one of the advances that's taking place right now is the ability to tailor and use tiered fibers, where the fiber path can be tailored as shown in the slide there, where we show a wing surface built by Aurora Flight Sciences, which is now part of the Boeing company. So there are tremendous advances, and that particular wing is now at the University of Michigan atrium because my colleagues and one of my former students was involved in the design. There are many parameters that go into the construction of a AFP type structure. There is the machine, the layup head, the slit tapes that are laid up to make the structure, and then the control parameters such as the tension in the tape, the temperature, etc. When we develop digital tools, we must be able to account for the effects of the manufacturing process on the finalized structure. So I'll be coming back to comment on this later on in my talk. Along with the tape structure, you are necessarily introducing length scales. All the way down from the molecular level, we heard talks at this conference where there were groups of researchers studying curing of a thermoset resin at the atomistic level. If you track that process all the way to the structural level, you will find that the material that we are working with has different length scales, starting at the atomistic level and going up in hierarchical order. The question now becomes, if you build digital tools, at what level do you encompass the details that you see in this process, and what are the effects of those details on a particular outcome that one is interested in? Textile composites are another type of a material that is of extremely useful for the aerospace industry. Here I'm showing examples of braided, 3D woven composites and a picture of an automated braiding machine. These types of automation allows designers to realize structures that they could not otherwise manufacture with traditional approaches. So the design space for composite structures is becoming larger as we adopt newer and newer manufacturing techniques. Along with the manufacturing process of textiles, again, you get length scales coming into the picture. You have, for example, here I show a 3D reinforced composite, and you can see that within that structure you get different toes. Within the toes you get fibers and matrix, and you have a binder toe that binds all the layers together. All of these details become important when we look at the performance of a composite structure, particularly the performance in fatigue, the performance when we want to look at ultimate loads, etc. Now, the building block approach is a mainstay of the aerospace engineering structural development process. This chart, taken from a paper by the director of Boeing BCA, Steve Chisholm, nicely captures what happens in the building block process. You have material property evaluation right at the bottom of that pyramid. You have design value development, where you do subscale tests. And then you have analysis, verification, and tests of a larger structure, including a final a load test for a final built airplane, for example. On the right-hand side, I show numerical or digital tools that attempt to produce or predict what can come out of a building block experimental approach. So, the final goal of a digital tool is to be able to replace that building block approach, except for the top pyramid, the rest of it using digital tools. If we can do that, it will lead to tremendous cost savings. Now, Steve Chisholm coined the term smart testing in that paper. I like that, because what it says is that you can combine selective tests with digital tools that are verifiable, that are validated, to save funds and save money, basically save dollars that are needed for unnecessary tests that we try to use to validate a design process. So, when you develop digital tools, the design process is accelerated, product development occurs faster, costs come down, and your design space also becomes wider. Furthermore, you heard in the plenary talk the need for attritable aircraft in the future. This quest, if we are going to win in developing attritable aircraft, digital tools become indispensable. Without it, it will not be cost effective to take on attritable aircraft. So, I show a smart pyramid building block, where every layer is a virtual test. Not a single of those layers of the pyramid are done using actual tests. They are all done virtually. So the word smart testing is appropriate for such a pyramid, perhaps except the last final test at the top of the pyramid. Now, digital tools have been around. In fact, the NASA 2040 roadmap calls for developing what is called integrated computational materials engineering. We have, not only myself, several others have added the word structures, because for this community, what we really need is not just integrated computational materials engineering. What we need is to design the material along with the structure. So, instead of calling it ICME, I think a more appropriate word is to use ICMSE, which encompasses all of the tools that we use in airplane and spacecraft design, which is structural analysis, manufacturing, having a material database, MDO tools, and integrating them to come up with a digital framework for accomplishing the design process. All right, so first I want to talk about digital tools for performance modeling. Now, many in the audience know that you just don't need to use sophisticated digital tools for every problem that you encounter as a structural engineer. For example, buckling, free vibration, and certain types of post-buckling problems, you don't need high fidelity. Standard finite element commercial software can handle these problems as long as you know what type of elements you're using, what are the correct boundary conditions, and so on. And for thin gauge structures, which is what aerospace is driven by, structural stiffness dominates these problems. So, you don't need sophisticated digital tools for those types of problems. However, when it comes to notch strength, open hole knockdowns, low velocity impact damage, compressive strength after impact, strength knockdown due to damage in stiffened panels, and there's a larger list, These are problems where you need an accurate depiction of progressive failure. If these problems are not solved properly with the proper set of digital tools, then you will not be able to exploit what these tools offer for the design process. Furthermore, if you speak to airframers at Lockheed, at Airbus, at Boeing, Spirit, and various other large airframe manufacturers, they'll all tell you that they cannot afford to have sophisticated digital tools run for several days. They're looking for trade studies and computations that usually run in a few hours. So the challenge to the community is, how can we develop digital tools encompassing the details we want to capture and yet have the codes run in a few hours for it to be useful for structural design? So I'm going to show some of the research work we did at Michigan and at the University of Washington over these last, I would say, 25 years, developing the tools that we arrived at. And the key here is to manage the balance between high fidelity on the one hand and computational efficiency on the other. All right, so the tools we developed at Michigan and Washington, I've given acronyms here. VMCM, which is a tool which is much faster than XFM. Multi-scaling tool called NCIL. EST is a tool that's heavily used by many. And recently, a smart meshing and failure mode decomposition procedure that I think is probably one of the best digital tools we've developed in my career with my students. Furthermore, I want to acknowledge another digital tool that uses multi-scaling, which is the NASA Glenn multi-scaling tool called NASMAT, based on the generalized method of cells, which was introduced a while back. And that tool now is at a level of maturity that will also enable very fast computations. Now, this map shows on the vertical axis the resolution or the fidelity of a model, and on the horizontal axis the numerical efficiency. What you want to be is to be towards the right of that graph, so that computational efficiency is very high, yet a little high on the fidelity so that you can capture the correct amount of fidelity. Now, if you can go right to the top, the right quadrant, that's where you will find the best tool. However, usually if you increase fidelity, your computational time will increase and you tend to go backwards. So on this chart, I have put references and I've shown a plot. It's a very important plot. It shows the number of CPU hours that a computation takes with, here I'm showing number of cracks. You can think of it as number of damaged features. Element-based finite element methods do not scale with the number of cracks. They stay flat. Whereas XFM type methods, they increase linearly with the number of features you introduce. So the conclusion is that XFM type methods are not practical for structural design or for progressive failure analysis of composites. Now, we developed this semi-discrete damage model SD2M along with all the other tools at Michigan and Washington, which are highlighted with blue and maize: VMCM, NCIL, I2CBM, EST, and the ESD2M. They're all published in the open literature. If you are interested, you can ask me. But that map shows where you lie with respect to fidelity and with respect to computational efficiency. So the key to this ESD2M model is the separation of failure modes and an accompanying smart meshing procedure. Now, the VMCM method, when I compare it to the XFM method, for those of you who are interested in some of the details, you'll see that in a XFM method, as your damage, let's say a crack, occurs in a structure and the computation proceeds, what it does is it keeps refining the mesh by increasing the nodal degrees of freedom. So what happens is what starts out as a x by x system ends up as a y by y system while the progressive failure is occurring. The result is that your solver that solves your standard Ax is equal to b problem, which you do in every iteration, starts to grow. This is what causes the computational inefficiency that you see. This is what ties up the computer for days, because the size of the problem is also increasing while you are solving the problem. What you want to do is to have a method that is independent of the features that you are introducing in the problem before you solve it. You don't know what the features are going to be. That's the challenge. And so that's why that plot shows that if you have element-based methods or the ESD2M method, you can find answers in hours. Yet your resolution is as high as some of the XFM type methods. So my conclusion is those methods are not good, they're not practical for structural applications. A word of caution and a word of encouragement for multiscaling methods. What are multiscaling methods? Multiscaling methods take a structure, which is a complicated composite structure. I'm showing here is a tank for storing hydrogen, it's a textile. And then the tank level is homogenized. It's analyzed as a uniform material, yet we know it's not uniform. What you do in the solver is at every integration point in your code, you start looking at the structure at ever increasing length scales. So the second scale is called the mesoscale, where you put details of the toes and the way in which the structure is built. And finally, within the toes, you have a fiber matrix unit cell, which is the microscale. What you do is you pass the strains at every level by solving a problem at every scale and passing the strains to the lower scale. And then, starting from the lower scale, you compute stresses and you pass the stresses back to the main solver. So this is a concurrent multiscaling method which will take time computationally. So your computational time goes up, your resolution is quite good, but we are not at a level where we can do this for large scale structural problems yet. At the end of the talk, I will tell you about some ideas I have for accelerating multiscale methods. The NASMAT code is another multiscale method. The one I showed you earlier is the NSIL method that we developed at Michigan. The NASMAT code is a plug and play type module that has been developed by NASA Glenn. The prime movers are Evan Pineda, Brett Bednarczyk, Steve Arnold, and Trent Ricks. And the advantage of this approach, this code, is that you can have several hierarchical levels and you can introduce several features in your analysis tool. Computational efficiency still needs improvement, so much work remains to make NASMAT as efficient as needed for composite structural analysis and design, and there is work that's ongoing to precisely address that. Now I want to show you some example problems using the tools that we've developed. First problem is the low velocity impact problem and a compression after impact prediction using EST. EST is a method we developed which uses shapery theory to model the nonlinear progressive cracking in a thermoset matrix. Right? Matrix resin materials, when they are subjected to shear, undergo microcracking. We call that damage because at the length scale of the cracks and the laminar scale that we are analyzing, those microcracks do not affect. The scales are separated large enough that the laminar scale, those cracks can be thought of as damage. However, when the damage accumulates, you reach a peak point where you get a macroscopic transverse crack. That's when your stress drops and your strain still increases. That's captured with the crack band method. So EST is a pre-peak nonlinear model for the matrix embedded with the crack band method. And that's coded up in any commercial code, any finite element commercial code with a subroutine that implements these features. Now in addition, we develop the I2CBM code at Washington, which has another added feature, which is that you can put crack spacing based on shear lag theory. You calculate it outside the code and you put it in as a crack tracking algorithm. That was a thesis of one of my students, Ashit Joseph. The model that we use for LVI analysis is shown here, standard finite element model. That is nothing fancy here. And here I want to illustrate the problem of impact damage and compression after impact. The model for the CI analysis is also shown here, where we model the boundary conditions, the rollers, the support that applies the load to the structure, etc. And here I want to show results. You can see that the predictions of the EST theory in this particular depiction I am showing you for different values of impact energy agree very well with the experimentally measured impact damage responses. I'll show you the delamination areas and cracking as well. But these overall macroscopic features are captured quite accurately with the EST tool. These are for 24-ply laminates. Now here's a movie that shows on the right-hand side the impact damage predicted by the EST tool, and on the left-hand side a high-resolution micro-CT image going from the top of the laminate into the interior, showing ply by ply what happens to the delamination areas. This typical rotating fan pattern is very difficult to capture in a computational tool. Thanks to my student Dr. Hugh L, he was able to refine EST to be able to do that. And he demonstrated that for different types of laminates as well as laminates of different thicknesses, for different levels of energy in a consistent manner. So the delamination shapes are captured very well, and the reason I say that is that for the problem of predicting compression after impact, you don't need a high resolution tool to capture each matrix crack. What you need is to capture the delamination patterns correctly, which is what EST does. Now, it also is able to capture the damage footprint for different layups, which is another test for a code. Can you do this when you change the layup in a laminate? And here you can see that both the experimental results and the EST predictions are well within the levels of accuracy that one would want for a predictive tool. When we go to compression after impact strengths, all done virtually. So the impact is done virtually, computationally. That computational model is then subjected to compression. You can see that for the different stacking sequences, and for different impact energies for 3 different layups, the prediction error in the strengths are within at most 7.5%, which is pretty darn good for a computational prediction, because these tests take quite a bit of resources. So we are very confident about EST as a tool to predict impact damage and to predict compression after impact. And here is a movie showing some of the details of the impact damaged specimen going again through a micro-CT full 3D high-resolution image, and on the bottom a corresponding finite element prediction of the same process where you go right through as shown in the sketch above. Again, the asymmetry in the damage, because once you impact a laminate, the symmetry with respect to the center line is destroyed. So when you apply compression, the asymmetric response is captured accurately by the EST tool as well as seen in the experimental predictions right there. Now I want to show you examples of the 3 features that are used in this EST2M model, which is a higher resolution model than the EST model. Here, the major objective is to be able to capture the interaction between delaminations and matrix cracking, which is not important for the compression after impact problem, but is important for the other problems that I alluded to. So here there are 3 areas that I want to emphasize. 1, a smart meshing strategy. 2, the fact that these materials do not have the same strength at every material point. I will be coming to that later in my talk because of the process that we use to manufacture them. Finally, the constitutive model, which is the shapery theory model that we use with the crack band technology that I talked about earlier. So, the smart meshing tool, the probabilistic modeling and the constitutive model all must go together in order to get the predictions that I want to show. Now, in addition, most of the damage modes are mixed mode. What that means is that damage is not occurring because the state of stress is uniaxial. In fact, most of the time these damage modes are occurring in a multi-axial stress state, which means that you must have a good mixed mode formulation in order to get the correct results. One of the keys is that when you have mixed mode formulation, when a damage zone passes a point, all the tractions in the cohesive law must vanish simultaneously. And that's assured with this new mixed mode formulation that we have adopted. So now I want to show results of the ESD2M model, which my student, by the way, also presented separately in another talk. What's very appealing to me about this prediction is, number one, everything you see here, in fact everything in my lecture, ran under 4 hours. 4 hours is the maximum time for any of the problems you see here. Number two, the details such as edge cracking that you see in the second picture in this quasi-isotropic tension test, which is real, is captured in the ESD2M model. The increasing in the crack density is captured, the splits in the zero fibers are captured, and finally the failure of the laminate, which occurs when the zero fibers rupture, is also captured, where the failure plane is not perpendicular to the load direction. That's a feature of progressive failure. When you have progressive failure in a composite, the symmetry that you have in your initial undamaged structure is completely destroyed. So what you have at every successive load step is an unsymmetric, completely general laminate. And that's the reason why your final failure in that inset that I've shown you looks the way it looks, with delamination, rupture, etc. Very unlike a metal specimen. Here is an open hole tension challenge that was presented to us by the Boeing company, showing the smart meshing tool, and I'm going to show predictions for this particular laminate. What is interesting is to see how edge cracking, splitting at the hole, is captured very early on. The splits occur almost at 50% of the ultimate load. But is that of concern? Absolutely not, because the splits do not have enough energy to grow until you keep increasing the energy. So just because you get a split at a notch doesn't mean the laminate is no good. If you look at the final failure load, it's almost twice the load at which the split initially occurs. We have captured the angle cracks, the splits in the zero plies, the transverse cracks, macro cracks, splitting cracks in the 90 plies, and finally the way the laminate fails. These were blind predictions that we did for these types of laminates. We did this as a function of the size of the hole to the width of the laminate, as well as keeping the hole size fixed and changing the width. Here I am showing you results where we kept the scales the same. So the ratio of the size of the hole to the width is kept the same. And these were done at the Boeing company. The tests were done at the Boeing company. We are able to capture the notch strength, hole diameter trend that you see in these types of laminates. Furthermore, we are able to capture the failure mechanisms very accurately in all 3 different scale tests. All runs took less than 4 hours. Finally, I want to show you a very challenging problem: delamination migration. Delaminations that start at one layer, they migrate to a different layer because they are energetically favorable. Here I am showing you these laminates where the testing was done at the University of Bristol by Stephen Hallett, Michael Wisnam and their co-workers. Showing you the mesh and the details of the layup. And what's interesting about this particular test is that the load deflection curve is non-monotonic. It has a first peak, the load drops, stabilizes, and then the load increases again until you get complete failure. The movies there show you our predictions, and on the right hand side we show you the actual pictures published by Green, Wisnam and Hallett, which show the migration pattern and the way the delaminations migrate along with the matrix cracks, which are very accurately captured by the ESD2M model. And here, next I want to show this same for the different scaling that we did, and you can see the experiments and the FE model are very much in tandem, showing the final failure of these types of laminates captured very accurately with the interaction between matrix cracking and delamination, and the migration of the delamination as well. Finally, I want to show you a single edge notch tension test. This is for a cross ply. This is a validation test. This is not to mean that people are going to use cross plies in airplanes. This is done to show that the model we've developed is able to capture the interactions between the notch, the layers of the laminate very accurately. Can I have the video, please? So what happens when you pull it is that you get at the notch localization, and you get splits going down the 90 plies. These are DIC results, and you get edge cracks coming from the bottom away from the notch and going up. And finally, you get delamination in a triangular region that you see, and then you get rupture because the zero fibers fail, which I'm going to show you next. So these are the pictures that you get in the experiments, and on the right hand side I show you the actual predictions by the ESD2M model. You get the delamination predicted correctly, get the matrix cracking and the evolution of the cracking predicted correctly, and finally you get the rupture also predicted correctly and accurately. The load deflection curves for different notch sizes is shown in the left top, and again we are well within the bounds of what one would expect for these types of laminates where we have different specimens. Now, one word of caution: when you do identical tests of these laminates, do not think that you are testing the same material. You're not, because as I said, because of the manufacturing process, the strength distribution in each laminate specimen is different. So what you have is a stochastic distribution of strengths in the laminate. And so when you do this virtual model that we are presenting, it is like doing tests, because each computational run uses a different strength distribution in the simulation. So Monte Carlo simulations is what allows you to capture that scatter. And you can see that the predicted scatter of the strengths between experiments and the ESD2M model is very good. And the pictures show the predictions against the actual coupon that you get in the laboratory. Now I want to switch gears to talk in the last section of this talk about textiles, textile composites. In textile composites, you start, and when you look at the process model, you begin to understand why the strength varies. The reason is, just look at that thick composite part. If you take 2 points, one point A on the surface and another point B in the interior. Now that is a 120 ply thick part. So there's 120 plies in the thick section. There is no way that the temperature distribution is going to be uniform during the autoclaving process. What does that mean? It means that there is going to be residual stresses. It means that the part is not going to cure uniformly, no matter how much you like it to be uniform. That's nature. That's the nature of the heat equation. As a result, the strength on the surface is not the same as the strength in the interior. Not because the fibers are at a different angle, it's because of the thickness of the part. So when you cook a thick part, you have a temperature distribution resulting in a strength distribution, which you have to account for to accurately capture progressive failure. All right, what else? You get defects. If the residual stresses are high, you can have cracking inside the structure before you put the structure into service. You can have wrinkling of plies, and you can have porosity if the gases that are within the resin at cure are not able to escape. If you don't account for this, you can get drastic differences between prediction based on virgin properties and predictions based on in situ properties, the properties of the actual resin that's inside the laminate. Can we predict this? That's the question. So if you want to predict this, you have to go to basics. You have to look at how thermosets cure. They cure by forming networks, and this network formation is governed by what is known as Kamal's equation for the network density. As the networks increase and get solidified, you get a solid developing from a gel-like material. Unfortunately, this happens in the presence of fibers. But before that, we have a collaboration with our material science colleagues John Kiefer, where we measured using Brillouin and Raman scattering how the plane wave modulus and the shear modulus evolve during the curing process, so that from that we can extract the Young's modulus and the Poisson's ratio of the resin during the cure cycle. Now, I want to emphasize that different cure cycles lead to different evolution of curing or solidification of the resin. So if you want to embed this in a code, what you need to know is how Young's modulus, Poisson's ratio, shrinkage strains evolve as the cure cycle progresses. Now, was it yesterday or day before yesterday, there was an excellent talk by Professor Mayaru and her group at Lowell, Massachusetts, who are not only doing this, but going to the molecular level to predict curing. So here's an example of just curing a block of resin with that temperature cycle. Initially, you get stresses developing in the resin, they relax, and then during the final drop in the temperature, you get shrinkage strains that set in, and the block solidifies. So you get tensile stress buildup during the cooling phase, which is the final phase in your cure cycle. When you put fibers and cure a toe, for example, you get a similar result, except now your heat transfer is going to be impacted because of the fibers. So here I am showing you our approach to homogenize and evolve composite properties, because we cannot afford to model every single fiber in a textile. So this is an illustration that if you use the proper homogenization process, you can get the thermal evolution problem solved for a toe properly using the inputs that I showed. Now, there are many tools that are out there. There's Convergent, there's PAM Composites, Siemens, ESI. All these tools provide residual stress and distortion of a part during the cure cycle. What we've done at the University of Michigan is we have a tool that does all of that, but in addition, it can also predict damage evolution during and after cure. So during the cure and then after, when you subject it to mechanical loading. Here I'm showing an illustrative example of a famous noodle problem where I used a cure cycle exaggerated to show how cracking can start near the noodle and then progress up. But if you change the cure cycle, you can suppress that cracking during the curing process. So the advantage of a digital tool is that you can do these trade studies to optimize your cure cycle for the particular structure before you set the manufacturing process. That's the reason you want to analyze this. Shape distortion and damage during the cure process. And you need a resin database. So Convergent, for example, has a resin database for standard aerospace resins, so does NIR, that shows the thermal property evolution during QO. Now, this problem is complicated. Damage and failure can also occur post-QO. So again, you need a crack band method to keep things mesh objective, and you need to have the ability to account for damage that can set in. So we've embedded our curing tool with the crack band method in order to do that. So I'm going to show you examples now of a project we did with GE, where we cured 8 harness satin weave textile composites at the micro level, where we made a 8 harness satin RVE. The RVE details are shown here. As I said, you cannot afford to model every single fiber at this level. So all the toes are modeled as homogenized evolving solids. And then you embed that in a matrix that's also evolving during the QO. We do these tests, virtual tests of tension, compression and shear. And now I want to show you some results and comparison against experiments. So video please. So here I'm showing you how the axial toes in a tension test in 8 harness satin will fail. As you pull it, the toes get stretched, and where you have they jump over, you get very high shear and tensile stresses, and you get fiber rupture. On the right, I'm showing you a picture of the exact 8 harness satin specimens with photoluminescence to show how the cracking occurs as well. So the digital tool is able to capture the localization and the failure that occurs in these textile composites. What's more important is to realize that if you ignore the QO cycle, you can get misleading values for the strengths. So you can see here in this plot where we did not QO, we did not include any thermal stresses, and we did virtual tensile tests. And if you include the curing stresses, you get a lower value because there's residual stresses in the matrix. Similarly, we show the same for compression. So different QO cycles will result in different strength predictions as well when you change the QO cycle. This is very important to understand for textiles. All right. So now I want to end my talk by asking a few questions of where are we heading. The NASA roadmap 2040 has many interesting aspects where digital tools will play a major role in the future of composite aerospace structures. I think personally, if we want to have high fidelity simulations but done very rapidly, I think the place where you will see a lot of gain is in machine learning and AI based techniques. At this conference, I heard 2 great talks. One was data driven damage initiation for carbon fiber reinforced polymer composites, where the speed of the Mohr-Coulomb criterion was accelerated by 130 times by using a machine learning deep neural network. A convolutional neural network for enhancing multi-scale localization in the GMC method of cells, which lacks shear normal coupling, was presented by Pete Gustafsson et al., shows tremendous gains in the computational efficiency. I think in the future, you will see much more in this line of thinking and in these types of tools that we will see for composite predictions. Finally, I want to say that there are codes, Dakota at Sandia and NESIS at Southwest Research Institute, that can do excellent jobs in uncertainty quantification. So we don't need to reinvent that tool. What we need to do is work with Dakota, work with NESIS to couple the finite element software so that we can get also metrics for uncertainty in the predictions that we do. And this is something I'm pursuing right now with both Dakota and NESIS. Thank you for listening, and I take any questions you have. Thank you.
Thank you for that exceptional lecture. So before we take questions, we are going to present you with the Dryden Lectureship Medal.
I was supposed to compliment.
Yes, you're good. There you go. Let's make sure we show the medal too. There you go. Very good. Awesome. Thank you. And now we'll take some questions. Sure. Have a seat. And if you haven't, you still have an opportunity to submit some questions here.
I tell students that if there are no questions, that's good. That means they understood everything.
No. There we have questions. What was the key enhancement made to EST to arrive at your new tool?
Great question. So the key enhancements were the smart meshing tool. It's an automated Python-based tool that if you give a structure and the layup, it's able to lay out a mesh where the mesh separates so-called matrix cracking elements from bulk elements that have the other failure modes. I think that's a real breakthrough aspect of that tool. The other is the recognition that for the longest time we were using deterministic values. And we realized that by using the same, for example, fracture toughness value without any distribution, we realized we were not able to get the scatter that we see in actual tests. So the second enhancement is the fact that we must use distributions for material properties when we do strength predictions for composites.
Okay, next question. How does the emergence of GPU processors in accelerating computational software play into the goal of producing software that provides the solutions in just hours?
I think the enhancements that you get with GPU are quite amazing. In fact, there are some colleagues of mine, I'm trying to talk to them, they are CFDers, and they're already using GPU enhancements to their CFD codes. I think that's happening already in some quarters. We haven't ventured into that with ESD2M or EST, but I would like to. I think that's the wave of the future.
Could these tools be used to evaluate cracks or damage in homogeneous metal, such as structural aluminum, for example, the Russian modules, which have impurities? That's a very important question.
That is a very important question. I have not ventured. I have to say that I can't remember the last time I worked on a problem where it was a problem of metal. I've been deadly focused on looking at fiber reinforced composites. I guess if you go to the granular level and you use crystal plasticity tools, there's a colleague of mine at Michigan who does that, there may be a possibility of using something like what we've done, but catering it to crystal plasticity. Metals at that level are amorphous, right? The grain structure is very random.
Especially with impurities.
That's right, exactly. So I don't have a good answer for that.
How does the emergence of GPU, actually, I'm sorry, we already answered that one. How does the analysis take into account imperfect manufacturing process?
Yes. So that's a great question. That's one of the reasons why we've done the processing module, because one of the keys, I think, to understanding Q cycle effects and optimizing the Q cycle is that the defect formations, such as wrinkling, for example, in certain plies at corners, that picture I showed you of a laminate that goes around a bend, where you get the fibers, the spacing between the layers widening. I think those details are important. And if you don't model the evolution of the manufacturing process and the way the part solidifies, I don't think you can get the defect structure properly. So that's one of the reasons why we've been focusing on modeling the manufacturing process before we apply the digital tool to look at mechanical performance. That's why we've been doing that. So I think that's an important area that we need to focus on.
Regarding the multi-scale analysis, can you accelerate multi-scale analysis by only solving at the microscale level in areas of high gradients while using more approximate methods in the other areas?
Yes, I would say the answer is yes. Okay. How you do it would depend on the problems, what you're looking for, what is your main outcome that you're driving at. So I think using analysis like the NCIL tool we've developed, the subscale is an analytical solution. So that accelerates your ability to exchange information between scales. Mm-hmm. If you do everything numerically, then it's going to slow down the process. Mm-hmm. But machine learning is, I think that's where the subscale problems can be replaced by response surfaces or a deep neural network that will allow you to get the macroscale quantities faster. Mm-hmm. So I think we are going to see more of that in the AIAA conferences in the future.
Okay. These models require many material property inputs.
Yes.
What gaps do you see in the characterization?
Great question. Mm-hmm. A major challenge is getting some of the fracture toughnesses that are operable inside the structure, duplicated in a simple test. I'll give an example. We talked about it yesterday in the ENF test, which is a standard for getting the mode 2 fracture toughness. The values you measure may not actually be representative of the multi-axial stress states that occur inside a laminate interface during impact, where we know the mode 2 toughness is a driver. Mm. How much you're off by in the real laminate, that's difficult to answer just by looking at the ENF values. The ENF values gives you a ballpark starting point. I think we have to do a little bit more with the data analysis, the machine learning type approaches, inverse modeling to get the actual data set that we need to use in the final outcome.
Okay. Do your tools take into account creep?
Thermoplastics, absolutely. Okay. We are doing some work right now with NGC where we are looking at thermoplastic manufacturing and post-manufactured virtual testing. Mm-hmm. And there, creep becomes a problem, especially when the temperature increases. Mm-hmm. So, yes.
Okay, just a couple more. How does the analysis take into account imperfect manufacturing processes?
If the manufacturing process is imperfect, so maybe you dialed in a particular cycle and an error occurred because the cycle that you thought you were putting to the part is not the cycle that you're putting in, or maybe you switched a ply. You have a 48 ply stack and the mid plies, the 24th and the 23rd plies are interchanged by accident. I really don't know a good way to detect that unless you have sensors that tell you. I know that the autoclaves have sensors and the parts have sensors to make sure that your thermal signature is correct. But the interior, that I don't have a good answer, how to detect such a defect. But the evolution of stressors and the formation of defects like wrinkling, those can be predicted. Yes.
Okay. How does the emergence, oh no, I actually got that one already. Oh no, how does the emergence of GPU processors and accelerating computational software play into the goal of producing software that provides the, oh, I'm sorry, I didn't answer that one.
Yeah.
Different one.
You passed that.
Okay, this is what I meant to look for. How do you see the future of AFP in competition with metal additive manufacturing in development of lightweight structures?
That's a great question. An AFP manufacturer told me that they may not be in business in 20 years. So if AFP is a prime manufacturer of machines that produce AFP, I think that's good, healthy competition. In fact, I think 2 of my students were telling me that they are looking at buying a 3D printing continuous fiber machine that can print small parts where you can have the fibers in a curvilinear path. Yeah. So if you can do that and scale that up, AFP is in for a good battle. So
you could do anything.
That's right. So I think there's going to be some innovations there.
Okay, and I left the best one for last. It's not even a question, from Carlos Sesnick. Tony, it was an excellent lecture, an overview of your activities in the field. Thank you, and congratulations on your Dryden Lecture Award.
Thank you. Thanks,
I think
Carlos.
we'll end with that.
Thank you.
Yeah.
Thanks very much.
That was great.